Okay, let's start our class. And last class, we already learned about this fundamental of channel encoding, type of channel code. In this, sorry, uh, in this channel code, type of channel code, there are two types of channel code, namely the block code and convolutional code. In the block code, there are some humming code and these things we already explained in the last class. That in the humming code, so we have n and k values that redundant bit are added to the k information bit to form the encoded bit. Okay, so each and every bit in the humming code having the parity check bit, this is the redundant bit. Okay, so this redundant bit connected to the information bit. And the next one is the convolutional code. Convolutional codes are one of the most widely used channel code in practical communication system. These codes are developed with a separate, strong mathematical structure. Primary and are primary sorry and are primarily used to real-time error corrections. Okay. In the communication, in the last class, we already explained that there's chance of error in this channel, in the channel, in the communication medium, maybe the physical or maybe in the wireless. The communication channels can cause the error itself and also from the external also. Maybe the interruption from the lightning or maybe a spark in the communications, and there's tons of interference, high tension line and high electromagnetic interference. Okay, there are tons of errors in the real times. That convolutional codes are one of the most widely used channel code in the practical communications. So this code is widely used for the channel code. These codes are developed with a separate strong mathematical structure. So it's having the mathematical constructions and are primarily used in the real-time error corrections. So real-time error corrections means during the time of the communications, if there are some error, then it's corrected instantly. But in the previous one, this block code is not the real-time communication, real-time error corrections. Okay, convolutional code convert the entire bit stream into one single code word. The code word bit depend only one of the current k input bit. So convolutional code convert the entire bit stream. Entire bit stream means there's lots of there are multiple of bit stream in the communication channel, and converted into one single code word means those bit stream are converted into a code word. Code word means some combinations of this error correction code, and there are some additional informations, redundant information is called the code word. Okay, and convert it into this. Okay, the thing is that if you transmit the voice or data, then those carrying this information is called this entire data stream. And apart from this data stream, we can add the additional redundant data for checking the data stream. This is called the code word. Okay, the encoded bit depend not only on the current k input bit. So this is the redundant. Okay, redundant bit, but also on the input bit. The main decoding strategy for convolutional code is based on the widely used Viterbi algorithm. So you have to remember this. The main decoding strategy for the convolutional code is based on this Viterbi algorithm. And let's see this algorithm. What is a Viterbi algorithm? The Viterbi algorithm is dynamic programming algorithm for finding the most likely sequence of hidden states called the Viterbi paths that result in a sequence of observed events, especially in the context of Markov information source and hidden Markov model HMM. So this Viterbi path is uh, based on the context of Markov information source and hidden Markov model HMM. So Viterbi algorithm is a dynamic programming algorithm. So algorithm is the function based on this some problems. Okay, so this based on the algorithm, the flow of the structure. Okay, the flow of the structure or programming code by finding the sequence of the hidden state. There are some hidden informations to finding these things. This is called the Viterbi. This Viterbi is based on the observations and the context of the Markov information source and hidden Markov model HMM. Number two, the algorithm has found universal applications in decoding the convolutional code used in both CDMA, code division multiple access, and GSM digital cellular, and dial-up modems, satellite, deep space communications, and 802.11 wireless LANs. So these Verbi algorithms are found universal applications in decoding the convolutional code. Decoding means in the universal communications means by using the common medium like a wireless or maybe a physical network. So it's use this convolutional code. What is the convolutional code? This is based on the Verbi algorithm. Okay, and this convolutional code is the decoding. Okay, applications in decoding the convolutional code used in both decoding the convolutional code used in both the code division multiple access. So what is code division multiple access? We have a multiple of channels from the tower. Okay, from the tower we have a multiple of channels in the mobile communications, in the cell communications. So each and every channel is having a code. Okay, each and every channels are having a code. So based on this CDMA, let me show you the example of this. Let's see here. CDMA. Let's check it out here in the picture. Okay. Okay, let's see here. Okay, here we have three types of multiple access system. One is the frequency division multiple access, and what is the time division multiple access, and another is the code division multiple access. In the frequency division multiple access, we have power and the time. Okay, in this power we have a different types of frequencies. The same time, at the same times we have a multiple of frequencies in the channels. Okay, so each and every channels having the communications, or we can have our communications based on each and every channels. But here we have our allocation of the frequency is very small. Each and every frequency have a different guard band, and we have allocations is very small. But in the time division multiple access, sorry, in the time division multiple access, each and every times we have a full allocation of the bandwidth. Okay, the full frequency we can utilize it in each and every time slot. But in the code division multiple access, we have different types of amplitude, the power of the frequency, and the frequency allocation, the frequency bandwidth. Okay, the spectrum, the bandwidth. We can say the bandwidth of the frequency. We can use it the complete. Okay, complete bandwidth of this. So these are the things. Each and every in the CADMA code division multiple access, we have a code for accessing those things. Let's see here code also. So from the base stations, okay, from the base stations we have different types of code. Okay, based on this code we can access the communications. Different types of code are allocated. Okay, different types of code are allocated. Then based on this code we can access the channel. Okay, these are the this is the example of this CDMA, and a GSM also explained in the class. Sorry. GSM GSM dial-up modems, satellite, deep space communication, and 802.11 is also wireless standard in the land. It is now also commonly used in the speech recognition. Speech recognition is commonly nowadays. Now this SR speech recognition is also embedded with the artificial intelligence and then you can communicate with the system also using the speech. And the next one is the speech synthesizer. So next one is the keyword spotting, computational linguistics, and bioinformatics. All those things, example of these communications, are based on these algorithms. Okay, let's go to the next point. Coding gain. Coding gain is what? In the coding theory and related engineering problems, coding gain is the measure in the difference between the signal to noise ratio, NIR. How many noise available in the original signals is called the SNR. Okay, signal to noise ratio. In each and every communications, we have to expect different types of noise. Okay, sorry. Different types of noise. In each and every communications, we are having this noise. Okay, this is called the SNR, signal to noise ratio. The level between this encoded system and code systems required to reach the same bit error rate. Okay, this is called the BER level. Okay, bit error rate when used with the ECC. Okay, in the last slide we already explained this error correction code. This is uh, error correction code is based on this okay, let me see. Okay, here in the interleaving, two types of the interleavings. We have the interleaving tools for error detections and error corrections, and ECC error correction code are designed to correct random error. So random error, not in the continuous, that randomly error is coming in the bit stream. Okay, it's coming in the bit stream. So this, okay, so this ECC is used in this code gaining. Okay, in the coding theory and related engineering problems, we have the coding gain in the measurements of difference between the signal to noise ratio SNR, a level between this encoded system and coded systems required to reach the same bit error rate level when used with this ECC. Okay, when used with this ECC. So for this coding gain, then this ECC is very important, this random error. Okay, let's go to the next point, turbo code. In information theory, turbo code are class of high performance for what error corrections. Okay, FEC, forward error corrections, high performance. That's very important. Turbo code are class of high performance for what error corrections. FCC is for the error corrections of high performance. Okay, so very fast and very efficient error corrections code. They were the first practical code to closely approach the maximum channel capacity of Shannon limit. So Shannon algorithm also there. Shannon algorithms. This is one of the algorithms for what? Code to closely minimize for the code rate. So up to approach the minimum channel capacities. Okay, Shannon is for calculating the channel capacities. Channel capacity limit. A theoretical minimum for the code rate and which reliable communication is still possible given a specific noise level. Turbo code are used in the 4G, 3G mobile communications. This error correction mechanism FEC in the turbo communications used in this 3G and 4G, or maybe in the UTMS and LTE, and in the satellite communications, as well as other applications where designers seek to achieve reliable reliable information transfer over bandwidth or latency constrained communications link in the presence of data corruption noise. So in the fast communications and the high application communications, data transmissions, okay, that's required a very efficient error corrections, error detections using this forward error corrections code. So this turbo code is very important. Turbo code compare with the LDPC code means low density parity checked, which provides similar performance. So for this FEC, we have the low density parity checks. Okay, parity check bit I already explained. Based on this LDPCs, we provide the similar performance. The name turbo code rose from this feedback loop used during normal turbo code coding, which was analogized, okay, to the exhaust feedback used for the engine turbocharging. So the name turbo code arose from the feedback loop. So feedback loop means it's during the communication channels, it's loop with the feedback mechanisms in the turbo code during the normal turbo code decoding. In the communication channels, we transmit the bit stream of data with the code word and it decoding those things using this turbo coding and from the feedback loop, from based on the feedback loop, okay, from based on the feedback loops. So these are the things under this turbochargings. Okay, now we complete those this unit 5, equalizations, diversity and channel encoding. Those turbo code and all these things are very important in the fundamental of the channel encoding. Okay, under this channel encoding we have different types. Okay, Verbi coding gains and turbo code in this channel encodings. Channel encoding, fundamental of channel encoding means we have a different type of channel for the communications. Okay, from the tower. So each and every channels having some mechanisms needed to have some channel decoding and error correction, all these things. So these are the fundamentals of this channel encoding. And another is this adaptive equalizers. Under this we have a training mode and rig server and interleaving. And what is the equalizations? Okay, these are the things under this unit 5. So